Okay, folks, we are on section 2.2 of your textbook here, Thermal Energy and Transfer in the Atmosphere. Just a warning, or a heads up, we're going to be using a calculator in the next week, doing some calculations on this stuff. Okay, so some of this you've seen before. Thermal energy is a movement of energy from an area of high temperature to an area of low temperature. And it occurs through radiation, conduction, and convection. That's how energy is transferred from high to low, thermal energy transfer. So we're going to look at these. Radiation, emission of energy as particles or waves. And we know it can be reflected or absorbed. And we looked at this with the electromagnetic radiation, okay? And we know that some of this hits the atmosphere and gets absorbed by gases. It gets turned into heat. Some of it is reflected, and we call that the albedo effect, the degree to which it gets reflected. Any substance at a higher temperature than its surroundings will emit radiate energy. So we can flash a infrared camera on somebody and they will give off heat relative to the cold air around them. And we can see that. Conduction, transfer thermal energy through direct contact. Particles with more kinetic energy collide into neighboring particles with lower energy. This causes the energy of the neighboring particles to increase. Conduction usually takes place in solids. And there we have it. One particle starts vibrating and it causes the other ones by it to start heating up. Conduction. Okay, finally convection. Oh, we're going to do conduction again. A burner radiates energy, radiant energy. The particles of metal closest to the burner absorb this energy and increases the kinetic energy. These particles then transfer the neighboring particles, causing increase in temperature. So this handle gets very, very hot as it conducts. We know that metal is a very good conductor. Well, how about this other concept of convection? Transfer thermal energy through movement of fluids. Fluids are anything that's a gas or a liquid. Movement of particles forms a current. Current is formed by the rise of hot fluids and the fall of cool ones. This is going to be very important when we talk about weather. It heats up, it rises, cools, it sinks. Ocean currents. So expansion of water lowers the density. Less dense will rise. When it contacts the cooler air at the surface, the water will cool and contract, and it will increase its density, and it will drop. Okay, so how do we relate this to weather? Local wind is caused by convection currents. Rise air warms, cools, and drops. Okay. Larger air currents are caused by cooler air being moved from areas of high pressure to areas of low pressure. Warm air is less dense than cold air. Warmer regions of the atmosphere exert less atmospheric pressure than cooler regions. Large convection currents are created between cooler and warmer regions of the globe. Now think about the equator being very warm. So we talked about the net radiation budget. If we're going to have an excess heat here, it's going to rise and then it's going to cool when there's a deficit at the poles. Coriolis effect. If the Earth were not spinning, there would be a continuous direct convection current north and south. However, since Earth is rotating, the winds are deflected either toward the right or the north or the left. The deflection is called the Coriolis effect. Okay, so in this first case, no rotation. We're just going to go up, convection, it's going to cool, it's going to go down. But because the Earth is spinning on its axis, remember it's spinning around like this, these winds are going to get pushed one way or the other, okay? And that's what we see. We get these different winds, okay, because of the deflection, because the Earth is spinning. They deflect. Global wind patterns. Convection currents in the atmosphere and Coriolis result in global wind patterns. Transfer energy from area of net budget surplus to deficit. If this did not occur, areas that were near the equator would become very hot, while the rest of the Earth would become much colder. Types of winds. We have trade winds located at the equator. They blow from northeast or southeast. They result from cool air from the north and south coming to the equator and the Coriolis effect. Now we get the westerlies located near the poles. They blow to the east. So they come from the west. And they result from warmer air coming from the equator to the north, south, and the Coriolis effect. Now, when I think about trade winds, where does that word come from? Trade. The trade blowing from the west to the east. And then the ships would move, get the westerlies, and they would come. And I've got this backwards. We're going to do it again. Trade winds are going from the east to the west, and then the ships would get winds that would bring them from the Americas to back to Europe. Okay, the trade winds would go from Europe to North America. Jet streams. Jet stream is a band of fast-moving air in the stratosphere. There's very little friction. Gas is up there, so it moves very quickly. Earth's surface and density of the troposphere produces friction, which slows global winds. Because of their high altitude, these winds are not subject to as much friction, so they move very quickly. Way above, and this is a picture of a satellite. That's a satellite, wing of a satellite, and up here, this is your jet stream. Very, very fast. Remember, the troposphere has got mountains and whatnot. The winds get stopped. And the jet stream usually dips down like so. Okay. Excuse me. Okay. Change in jet streams affect the formation of severe weather. Movement of jet streams, particularly in polar regions, can also affect the movement of air at the lower levels. Changes in the jet streams are therefore very important predicting weather. And I'm thinking that that picture I showed you of the jet stream dipping down, it actually dips even further down now with climate change. And that's affecting moisture, how much area is getting rain or too much rain, that sort of thing. Okay, I want you to do these questions here on page 379. And they are not on page 375, rather. Yeah. Yeah. Okay, and we'll end it there.